and 3 dimensions. So let's start by considering circular ripples spreading on a pond. So your textbook, the cover of your textbook has a picture about this. So you can see that when an object hits the surface of water, we all have seen these ripples form on the surface of the water. So this will be basically waves that are propagating, circular waves that are propagating in 2 dimensions, right? And if we were to kind of draw the profile, if we were to cut this, the water, or put some kind of device to record the amplitude of the wave, we'll see that this is a trough, then this is a crest of the wave, and then down here we're gonna find another trough, etc. So for waves that propagate in 2 dimensions, since it's cumbersome to try to depict them in 3 dimensions, so what people choose to do is they only draw the location of the crest of the wave. So if we drop something here, a rock or droplets of water or something like that, as we saw in the picture and we all have seen in real life, waves propagate in a circular way, they propagate out, and what these circles are representing are at a particular moment in time. This is like taking a picture of the pond at a particular moment. At this particular time, there are crests, the wave has crests, and the crests are what they're choosing here to represent with these circular lines, right? This would pretty much be a simplified representation of the picture of a pond that has these circular waves propagating. So when you take a picture, there's some points that are going to be higher and other points that are going to be lower than the average surface of the water, and these lines represent the location of the highest points or the crest of the waves. The distance between one crest and the next one is represented here where with the letter lambda, which, as you learned before, is the wavelength of the wave. So that distance, you can measure that distance between any two crests or wave fronts, which is a wavefront, as you can see in the picture, is the location of the crest of the wave. So each one of the circles represent the wavefront, and the distance between two wavefronts is what we call the wavelength of this wave in 2 dimensions. Now, one thing that sometimes we'll consider, especially in in chapters that are coming regarding optics, is that we're going to look at the case or the limit when these circular waves have propagated for a while, for a long time, and were far away from the point where they were produced. So if the source of these waves that we're looking at here in this picture, if that source is really far away, so that source would have produced circular waves. I'm not drawing the whole circle, but if that source is very far away, then by the time those waves arrive to where we are, they look pretty much straight. So in the limit, when the source of a circular wave is very far away, then we call those waves, those wavefronts, we call them a plane wave. So these lines are representing the crest of a plane wave propagating to the right. So these lines are the crest, and the distance between those lines is the wavelength, as we said before. Now, if you of course, we don't live in just in a 2-dimensional world. So in a 3-dimensional world, waves are going to propagate in a spherical manner. That is, the waves emitted from, say, a light bulb or a loudspeaker, they're all going to propagate in 3 directions at the same time. They're going to propagate starting from the point where they produced, and they will grow out. They will propagate out as a spherical wave. So I have a little picture of that, or a little movie of that. Not here, sorry. Here. So You can see here, they're depicting here maybe in black the crest and in white the trough of the wave, and the waves are propagating in the middle of this sphere, and they're propagating out. So this is what we call a spherical wave. So again, if we are far away from the point where these waves were produced, then the waves, when they approach the location where we are, the waves are going to look like plane waves. Okay, so this is the term that we're going to use. Plane wave is the term they're going to use to represent these waves, where the crest of the wave can be found everywhere on this plane, or this plane. Every plane here represents the location of the crest of this three-dimensional wave that is, say, propagating to the right. And again, the distance between those planes, which are related to the crest of the wave, that distance between one crest and the next is what we call the wavelength. Now, especially for chapter 17, when we're going to be talking about the phenomenon of interference, which is very, very important regarding waves. So to understand that chapter, we're going to need to understand very well the idea of phase and the idea of phase difference. So what is the phase? So when we're talking about a sinusoidal traveling wave, we said in a previous video that the wave could be represented by a mathematical function of x and t, and we wrote it as a sine of kx, and if the wave was propagating to the right, we said it would be kx minus omega t plus some initial, what we call the phase constant. So the number that we have, or the quantity that we have, the argument of the sine function, it's an angle in radians, and that argument of the sine function is what we call the phase of the wave. So that whole thing that I circle here in red, we're going to call it the phase of the wave. Notice the difference between the phase of the wave and the initial phase. So the phase of the wave is just phi, the initial phase is phi naught. Okay, so the phase of a wave tells us at that specific location x, at that specific time t that we chose, the phase tells us in what part of its oscillatory motion is the wave. Remember that a wave propagates in a medium, and that every point in that medium, every point in a medium vibrates, it oscillates back and forth. So when you have, for example, a wave propagating in a string, right? Let's say that we attach a string to a wall or something like that, and when you're shaking this string, every point in that string is moving up and down, up and down. So when we take a picture at a particular time and we look at one point on that medium, well, that point in that medium is going to have a certain displacement from its equilibrium position, and every point, as we said, goes up and it goes down. So the phase of the wave at that point, at that time, tells us where is that point, in what part of the oscillation that it's always doing, in what part of the oscillation that point is. So, for example, if I show you a picture of a wave propagating, so at this particular moment in time, the wave looks like this, I can ask you, what is the phase of the wave at this point? So remember that this wave is represented by a mathematical function that is a sine function, is an amplitude a times the sine of, and I'm going to just write this, the whole thing, kx minus omega t plus phi naught. Remember that we just define it as the phase. So if I know that the displacement at that particular location, if I know that the displacement, the location in the vertical axis of this point is at the amplitude, is the maximum displacement a, I know that this phase has to be pi over 2, because sine of pi over 2 gives you 1, and 1 times a gives you a. So at this point over here, we can assign a phase of pi over 2. So knowing the phase allows us to know at that point, wherever the phase has been indicated, what is that point doing at that particular moment. Is it all the way to the top? Is it all the way to the bottom? Is it in the middle? Is it somewhere else? So for example, if this point has a phase of pi over 2, what phase does this point have? So at this point, the displacement of the wave is 0, because we are on down here in the middle, which is where we choose to have as y equals 0. So this tells us that the sine of phi should be equal to 0, and we said in a previous video that this gives us two options for phi. Phi can be 0 or phi can be pi, but 0 is the actual answer here, because the way the wave or the function behaves after this point is to increase, to go up, and that only happens when you're starting from 0, and as you increase the angle, the sine function also increases. If the angle had been pi, so if you think about an angle of pi and you increase even further, the sine becomes negative. The sine of, say, pi plus 0.1 is a negative number, because sine of pi is 0, but if you go with an angle bigger than pi, the sine, you're in the third quadrant, and the sine is a negative number. But that's not what's happening here. If this is phase equal pi, as we move this way, the phase increases, because remember that the phase is kx minus omega t plus phi naught, and we're talking about this being the x-axis. So as we move in this direction in the x-axis, we're adding more of this, which means that the phase increases. If this was pi and we move this way, we're increasing the phase, but increasing beyond pi makes the sign negative. So the answer is that this has to be 0 phase. So this point over here has 0 phase. This point over here has a phase of, we already said that, pi over 2. Pi over 2. If we continue to look at other points, for example this one, notice that here we have a point where the displacement is 0 again, and we said that only 2 points had that only at 2 points the displacement could be 0. Those, or that at only 2 values of the phase the displacement could be 0. We already did phi equals 0. The other one is phi equal pi. So this point has a phase of pi. Again, that's consistent with what we just said, because as we increase the variable x to the right, then the sine of pi plus something becomes negative, and that's exactly what the wave is doing. It's going down towards the negative y-axis. So again, this point over here has a phase of 0. This point has a phase of pi over 2. This one has a phase of pi. And what do you think the phase of this point is going to be? Right here, what is going to be the phase of that? Again, we briefly discussed this in another video. This would be 3 pi over 2. You could also specify the same angle. You could specify the same angle by saying that it is minus pi over 2. It's not like these two are two different options. They are the same angle, right? When you measure in an angle, you can go this way and call that angle 3 pi over 2, or you could start here and go in the negative direction and call that minus pi over 2. Same angle. We're talking about this angle here. So for this point, we can assign a phase of 3 pi over 2 or minus pi over 2, etc. At this point, we can call that 2 pi, or we can go back to calling it 0, as we did here. Phi equals 0 at this point. You can call this one also phi equal. You can call that one also phi equals 0, or phi equal 2 pi is the same angle. All right, so Let's go back to what we said before. So if that is the phase of the wave, noted as phi, then an important concept derived from that is the phase difference. So let me erase here. What's the phase difference? So the phase difference between 2 points, we're going to denote it with delta phi, phase difference. So delta phi, the phase difference between 2 points on a wave, depends only on the ratio of the separation, delta x, to the wavelength. So the reason is because delta phi literally means take the phase of one point and subtract the phase of the second point. Now you might not be seeing right now, you might not see what's the importance of this. Why would we want to take the difference between the phase of the wave at one location and the phase of the wave at another location? What is that? How is that useful? Well, this is in chapter 17. We're going to see that this concept, the difference in phase between two waves at a particular point in space, it's a crucial quantity that determines whether the waves are going to interfere constructively or destructively. So in this chapter we can introduce the idea of difference in phase. Although we only have one wave, we can still talk about the difference in the phase of the wave at two different points. So what is the phase of the wave at this point? We call that phase phi 1. What is the phase of the wave at this point? We call that phi 2. And we're interested in finding what's phi 1 minus phi 2. What's the difference in phase between those 2 points? Now the phase of one point on a wave, as we said, is kx minus omega t plus phi naught. Since we're talking about the same wave, then at a different point we have a different x. The omega and the time are the same, and the initial phase is the same. So when you take the first quantity, k x1 minus omega t plus phi naught, and you subtract the second quantity, k x2 minus omega t plus phi naught, you'll find that the terms that are equal are going to cancel. So this minus omega t and this minus omega t are going to cancel. Notice that there's a minus difference here. And the phi naught and the phi naught over here are going to cancel because you end up with phi naught minus phi naught. And the only thing left is the wave number multiplied by kx minus, not kx, x1 minus x2. So what is k? The wave number is defined as 2 pi over lambda. So we have arrived to the equation that delta phi is k delta x, which is the same as 2 pi over lambda times delta x. So if you ask yourself what is the difference in phase between two crests that are adjacent, between this point and this point, what is the difference in phase between those 2 points? What's delta phi? The answer is going to be that the difference in phase is 2 pi. The reason is that in our equation right here, when the two crests are adjacent to each other, the distance between them, the delta x, is lambda. So delta phi, in that case, here. So in that case, we just have to replace delta x with lambda. So this is going to be delta phi is going to be 2 pi over lambda. And what is delta x between this point and this point? A distance have a special name, which is lambda. So delta x is lambda, and notice that lambda and lambda cancels, and you get 2 pi. So we say that the difference in phase between two adjacent wavefronts is always 2 pi radians. All right? All right, let's move on. So just to check your understanding about that, let's take a look at this question in your what's going on? Let's look at this question in your textbook. It says, well, it's showing you a spherical wave that is traveling outwards from a point source. What is the phase difference between the 2 points on the wave marked with dots? So you can call this one phase here. You could call it phi 1, and you could call this one the phase, or the other way around. Let's do it this way, phi 2, and this point, the phase of that point, we could call it phi 1. What is the difference in phase? What is phi 1 minus phi 2? So it seems like you don't have enough information, but notice where these 2 points are located. This point is located between this crest and another crest, right? This point is located between one crest and the next one. We already said that between 2 adjacent crests, there is a difference in phase of 2 pi. So if the difference in phase between this point and this point, if the difference in phase is 2 pi, then the difference in phase between this point and that point must be half of it, because it's halfway between those 2 points. So the answer is that the difference in phase should be pi radians, half of the difference in phase between 2 adjacent crests. Alright, that's all I have for you. See you in the next video.